Good morning, everybody. Manage participants. Chat. Going to give people a couple minutes to join. While people are joining, let me show you something that I just set up. Not that. Close. So if anybody has Microsoft OneNote, I'm going to start doing sort of these online Zoom lectures using Microsoft OneNote. And down at the bottom, grab my little handy dandy thingamajiggy, bam. So I have a little link that I added. So this will be a link to the online OneNote notebook that I have. So this link, OneNote, if you have Microsoft OneNote, you click on it and it'll bring you to the most up-to-date version. I think every time I update the notebook, it automatically uploads it. And then when I'm done everything, it'll open up a PDF. Or when I'm done everything, I'll upload a PDF of that. And just to show you for the Microsoft OneNote. So what I'm going to start probably doing for the Microsoft OneNote notebooks and what I'll be using for these online Zoom lectures is Microsoft OneNote, and I will throw in my lecture notes that I personally would use. So this is just a Word document that I can then annotate. I will also include the clicker questions so that we can sort of do the clicker questions together as a class. And then PowerPoint slides, I will throw those up there and kind of use those in lecture also. And then anytime I'm doing diagrams or something like that, I'll open up a new tab. So hopefully this will be a useful resource. So if you click on that link at the end of lecture today, I'm pretty sure it will bring you just to all the updates I made. And then when I'm done chapter 23 as a whole, I'll convert the entire thing to a PDF and then share that. Good morning. So before I do a little recap, any questions about anything involving physics 10? Let me just say one thing. I had a question or two. After you do the homework, it's going to show your grade is a 0. And that's just because those questions are essay questions and I have to grade all the essay questions by hand. So I don't know if I'm going to actually take the time to, the way the instructor program is set up is it randomizes the student answers, it hides the names, and then it just lists all the questions for each, all the answers for each question, and you can grade them individually. I think I'm just going to quickly glance over each person's homework assignment and then just give you a point. So I don't think the master in physics is going to be updating your homework grades, just to let people know that. Again, it's going to be like before. It's either full credit, no credit, or half credit if you tried most of it. So before I sort of start on a little bit of a recap of chapter 23, what we covered so far, are there any questions I can answer about anything? Going once, going twice, bringing out the recap. Okay, so one, let me bring up our simple circuit. Bring this up for a second, share, whoops. Share screen. So this chapter, chapter 23, is just all about electric circuits. And the very most basic circuit, so I just went to Google, I did a Google search for simple circuit. all you have for most simple circuits, you'll see exactly the same thing. You got this to annotate. So every simple circuit basically consists of some sort of device which is supplying electrical energy, the battery. You have two wires. These are conducting wires. And the electrons that move inside a circuit are the electrons that are already present in the wires of whatever you're connecting your electric devices to. And then you've got an object, which is basically converting electrical energy into some other form. So right now, we're basically going to be looking at light bulbs. A light bulb is taking electrical energy, converting it into light and heat. And then in general, you have a switch, just so you can turn the circuit on or off. You represent it different ways. If you were to take a mathematical course where you start drawing what's called circuit diagrams, a battery, you either draw with a longer arrow or a longer line and a shorter line, or sometimes you draw it with two sets. So this is how you would represent a battery if you were drawing a circuit diagram. A light bulb is usually just a circle with a little X in it, and then the switch you've got just kind of looking like that. So let me go to this, see if this new share works. New share, no. Can I, let me go to, stop this share for 1 second. Go back to this construction kit. Start this share again. Okay, so this is a cool little program. If you wanted to try this out on your own, if you do a Google search for PHET, P-H-E-T. One, there's all sorts of great applets. Some of the ones I showed you in class are from this site, PHET circuits. You Google that and you'll find basically this where you can start playing around. Let me undo this. So here is my simple, just clear all drawings. Here's my simple circuit is I have a battery. Battery's got a positive terminal and a negative terminal. I've got some conducting wires, and there's already what's called free electrons in the conducting wires that aren't anchored to any particular atom. This I'll talk about, this is just a resistor. This is just something that has a known resistance, which is used to control the amount of current in a circuit. And then here's my light bulb, and then my switch. When I close the switch, when I close the switch, now what I have is I have a complete circuit. The battery supplying the force to move the electrons that are already in the circuit, and the electrons are moving from the negative terminal to the positive terminal. So wait, why is this not lighting up the battery? Or not, why is this not lighting up the light bulb? Do I need more current? Let's see. Interesting. Anyway, for some reason, the light bulb is not lighting up. But few things to notice about this. One, this is a little slider. I can control the voltage of the battery. And it's just kind of like, in a sense, having a battery where you can tweak it from 1.5 volts to 20 volts or whatever. I'll talk a little bit more about what voltage is, but the big thing you want to keep in mind, the more voltage, the more current. So you can see as I crank up the voltage, now I have more electrons moving faster. I've got a bigger current. And let's see what happens if I keep cranking it up. So we'll talk more about this, but as you get more and more current flowing in a wire, the wire heats up and you can have bad things happening. So the other thing is we're going to talk about more, but bigger voltage, bigger current, think about that. And this right here is something called a resistor. And it has a specific resistance that we'll talk about, but the bigger the resistance, the less the current. So if you notice here, let me crank up this a little bit more. So I've got the voltage is 20 volts. In this case, the resistance, don't worry about the numbers yet, but it's 5 ohms. As I increase the resistance, which you see is the higher the resistance, the smaller the current. And just as a preview, what we're going to be covering, and I mentioned this before, Ohm's Law is sort of the big law that deals with current. And it says how much current you get is equal to how much voltage you connect the circuit to divided by the resistance of the circuit. So we're not really going to be using this equation to calculate numbers, but let's just make these numbers easy for a second. Mouse. So let's make this voltage 10 volts. And let's make this 10 ohms. So like if I wanted to know how much current I was going to get, one, again, this is a big preview, but one current we usually write as the letter I. Voltage we usually write as the letter V. Resistance we write as the letter R. So in this case, if I have the battery has a voltage of 10 volts, the resistor has a resistance of 10 ohms. 10 divided by 10 is 1. I should have the current being 1 amp. And hey, I have a little current measuring device. This would be called an ammeter. It looks nothing like this in real life, but I measure it. Hey, I have 1 amp of current. This is what I would expect from Ohm's Law. So then, quick little question for you. Before I do this, I'm going to now change the voltage from 10 volts to 20 volts. What do you think is going to happen to the current when I crank up the voltage to 10 volts? Think about that for 10 seconds while I have some coffee. And the answer is if I double the voltage and if I double the voltage and the resistance doesn't change at all, the current should double. So if I double this voltage from 10 to 20, what you see is that my current went from 1 amp to 2 amps. So if instead, so let's bring this back to 10 volts. So 10 volts divided by, in this case, the resistance is 10 ohms, gives me 1 amp. If instead I somehow increase the resistance, big thing to keep in mind. Hey, somebody drew on that, awesome. Bigger the resistance, the smaller the current. So in this case, if I crank up the resistance from 10 to 20 ohms, what's going to happen to the current? Well, in this case, it's going to go down. So now if the resistance is 20 ohms, I have a more resistance, less current. It's just like it sounds. Resistance is resisting the flow of current. The more resistance, the less current is going to flow. Ha-ha, little arrow there. So that's sort of the big picture. The big things in this chapter are this simple circuit, understanding what current is, what resistance is, and things like that. And then we're going to get to series and parallel circuits. So let me stop this share and open it up for questions for 30 seconds or a minute or two, anything about that. If not, then I'm going to sort of just go into chapter 23. I've already done a little bit yesterday, or not yesterday, Tuesday.
So you said the bigger the resistance, smaller the current?
Yes, bigger the resistance, smaller the current. Okay. So what we say is that current depends inversely on resistance, like 1 over resistance. Resistance goes down, current goes up. Resistance goes up, current goes down.
Sweet, thank you.
Yep, and then something that'll just be important later. For a wire, as current flows in a wire, the more current, the hotter the wire gets, which means that the current in, well, that's a homework question. I'll let you think about that. We'll actually talk about that a little bit more. But if the resistance changes, then the current changes. Okay, other questions I can answer. Okay, let us move on. Let me just get this OneNote set up. Clicker, PowerPoint, that's what I wanted. Okay, so before I was just talking a little bit about the analogy between the flow of water and the flow of electricity. It's really hard for people to picture electrons moving in a circuit, so oftentimes we give the analogy of water flowing. Now, if I have water in a pipe, water is going to flow from higher pressure to lower pressure, right? That's just the way things work. The more pressure there is, the more force there is. So anytime there's a difference in pressure, there's going to be a force pushing things from higher pressure to lower pressure. So if I have, let's say, water like this, let me get a different color to annotate. And let's do green. So water, the deeper it is, the more pressure there is. So this water down here is deeper than this water down here. So I have more pressure on this side, less pressure on this side. Water is going to flow from higher pressure to lower pressure. But what's going to happen is very quickly, the levels would equalize. There would be no pressure difference. Water would stop flowing. Not ideal if you're thinking about, I want this continuous flow of electricity or this continuous flow of water. So how do you alleviate that situation? What you need is something that's going to maintain a difference in pressure by taking water from lower pressure to higher pressure, taking water in the exact opposite way it would normally want to flow. Let me change this again. So normally water is going to flow from higher pressure to lower pressure, but what this pump is doing is it's taking water from lower pressure and bringing it back up to higher pressure. So I'm constantly maintaining this difference in pressure. I'm reviewing this again because this is exactly what a battery is in terms of what it's doing. So for a battery, you have what's called a voltage difference, a difference in electric potential. I'm not going to cover voltage the same way your book does. The way voltage is defined, and let me just write it to be clear, voltage technically is equal to electric potential energy. Can I write on that part? Potential energy per unit charge. And in terms of units, if this is important to you, if not, don't worry about it. 1 volt is equal to 1 joule per coulomb. Meaning for every coulomb of charge that passes through a battery, it gets a potential difference of 1 volt. Don't worry about that. Think about this. The pump is maintaining a difference in electric potential between the two ends of a pipe, let's say. And so an effective pipe could maintain a bigger difference, an effective pump could maintain a bigger difference in electric potential. Well, what a battery is doing in essence is maintaining that difference in electric potential and maintaining that difference in electric quote unquote pressure. So the bigger the pressure difference, the more the water is going to flow, the bigger the difference in potential, electric potential or voltage, the bigger the difference or the more electric current is going to flow. So think of a battery as just an electric pump that's maintaining a difference in electric potential. That's really what I want you to know about voltage. So the pump is the same thing in a circuit as a battery. The valve is basically something that controls the flow of water, same thing as a switch. And a resistor is a section of wire that's hard for current to get through, or a little device that's hard for current to get through. The analogy in a pipe would be like a jagged line where it's hard for the water to flow through. Not a perfect analogy. Okay, so let me go to lecture notes. Okay, so kind of pick up where we left off. Current is just the flow of electric charge flowing from one spot to another. In general, it's electrons in a wire that's flow, and current is defined as how much charge flows past a given point in a given amount of time. So if I had let me get you 1 second. If I had a wire and I have a bunch of little electrons that are flowing in the wire, and I looked at a certain area and saw how many electrons flowed past this point in a given time, that's what we call current. And current is measured in amps, and an amp would be 1 coulomb of charge flowing past a given point in 1 second. And let me just say, an amp is a huge amount of current. I didn't go through this too much, but the charge on an electron is really, really small, 10 to the minus 19 coulombs, which means 1 coulomb of charge is the charge on 6.25 billion electrons. So an amp is a huge amount of current. We often deal in milliamps, which is a thousandth of an amp, or microamps, which is a millionth of an amp. All right, let me pause. Alana, you had a question.
It's not so much a question. Can you zoom in on the screen? It's really hard to read the type.
Ah.
Thank you.
Does that work?
Yeah, that works.
Okay. Okay, a couple things. Wires are normally neutral. Just because a wire has current flowing through it does not mean it's charged. So this little note, whether a wire carries a charge, current or not, the charge is normally 0 because the wire itself is generally neutral. It has just as many electrons as it does protons, but some of those electrons aren't anchored to any particular atom. They're wandering around the wire and basically just kind of freely moving around. It's only when you connect it to a power source like a battery that supplies the force to move electrons in the circuit that they start moving. So I've talked about this electric potential. Come on, mouse. I can't figure out how sometimes, oh, I know, let me see something. If I draw on this, then I can erase. Ah, I just figured something out. So if I want my writing and stuff to stay on the notebook, I need to do the annotation in Microsoft OneNote and not in Zoom, which makes complete sense. Okay, so we were talking about just electric potential. Here's the keys to know about this. If I want to sustain the flow of electric charge or current, I need to have some kind of pump that's maintaining a difference in electric potential. Just like a water pump maintains a difference in water pressure, an electric pump maintains a difference in what's called electric potential. But don't even worry about electric potential. Just think about it as electric pressure. The bigger the difference in pressure between two ends of a wire, the more current's going to flow. The bigger the difference in pressure with water at two ends, the more water is going to flow. So what is a voltage source? A voltage source is just something that's maintaining this difference in quote unquote electric potential. So in essence, a battery or a generator. Now we measure voltage in the units called volts. And I mentioned before, 1 volt is 1 joule per coulomb. But do not worry about that. Again, just know that more volts ultimately is going to mean more current. So here's our simple circuit again, is I've got a voltage source, something which is maintaining a difference in electric potential, electric pressure. So in this case, I'm just drawing the battery like a battery. We've got always the little nubby part is the positive terminal. The little other part is the negative terminal. Once I complete the circuit, I'm going to have electrons flowing from the negative terminal to the positive terminal. And what we know is that, like I was saying, the bigger the voltage, the more current flows. So what this means is this particular circuit right now with a 6-volt battery is going to have a certain amount of current in it. I don't know what that current is unless I know the resistance. But what I do know is that a 12-volt battery is going to produce twice as much current as a 6-volt battery. So first thing is that how much current flow. Let me make this a little bigger too. So how much, oh, I wrote it right here. How much current we get is directly proportional to the voltage. If I double the voltage, I double the current. So if instead of using a 1.5 volt battery, I use 2 of them and I have 3 volts, I'm going to get twice as much current as if I only had 1.5 volts. So first big piece of sort of new news, but not completely new. How much current you get is proportional to how much voltage you are connecting the circuit to. And again, just think of voltage as electric pressure. A battery is just maintaining a difference in electric pressure, causing current to flow from higher voltage to lower voltage. Now, how much current flows also depends upon what's called resistance. Everything resists the flow of current flowing through it. How much a particular wire or light bulb or resistor or electrical device resists the flow of charge, the more resistance it has. We have a unit for that. It's called ohms. And again, you don't really need to worry about what the unit means, but the bigger the resistance, the less current, the lower the resistance, the more current. So let me pause this for a second. Stop this share. I want to open back up this simulation. Screen share. Okay, so going back to this simulation. So one thing that's not realistic is if I click on these wires. Okay, it doesn't even give me the option. So wires themselves do have resistance. Oftentimes, if you're dealing in a lab, like if you were taking an electronics lab, oftentimes you ignore how much resistance the wires have because it's pretty low. And just to give you an idea, it's on the order of 10 ohms or less, something like that. In this case, I thought I might be able to adjust what this wire is made of, maybe make it bigger or smaller. I can't. The reason I wanted to do that is because how much resistance a wire has depends upon some certain characteristics of the wire. But I can't adjust these. So just so you know, in this particular animation, all of these wires are in a sense perfect conducting wires. They have no resistance. That's not realistic. But what I showed you before, just to do it again. So right now, this battery has 10 volts, which means it's supplying a potential difference of 10 volts between the positive terminal and the negative terminal. Again, don't worry about that. It's just maintaining a difference in electric pressure. So without worrying about the resistance right now, current depends upon voltage. Again, the relationship is annotate, draw, current. Ugh, that's a horrible color. Current is proportional to voltage. Or your book writes proportional as, oops. Your book writes proportional as that little squiggly line. So if I now double my voltage to 10, 20 volts, so right now the current is 0.5 amps. If I were to double the voltage to 20 volts, my current doubled. So more voltage, more current. And that's all I gotta say about that. Let's go back to lecture notes. Okay, so I kind of have the answer here, but in class, I would have asked you this sort of as a group question. So let's say I have 2 different wires. And let me go to draw on this. So I have one wire, which is, I can do it right here. One wire, which is really, really thick overall. The other wire, which is really, really thin. And if I think about resistance, is how hard is it to get from one end to the other? Well, if you imagine just a bunch of electrons trying to get through this wire, the more room there is for them to move, the easier it's going to be. which means it's probably going to be a lot easier for electrons to move through a big fat wire than it is a very thin wire. So the first characteristic of a wire that the resistance depends upon is the thickness of the wire. Thicker wires have less resistance just because it's easier for electrons to flow through a thick wire. If you think about just instead of electrons, bunch of people trying to walk through a hallway. If I have a nice big fat hallway, it's going to be easy for people to walk side by side. But if I have a really skinny hallway, it's going to be much harder for people to get from one end to the other. So for a wire, the thicker the wire, the less resistance there is. Second thing is how long the wire is. So part two, how long, let me kind of think about up here. So let's say I'm trying to get, so here's a circuit. Whoops. So here's my battery. And let's just say I'm trying to get from one end to the other. If I just have one little, well, I should put a light bulb in. Here's a path right there. The reason I should put a light bulb in is because if you were just to connect one end of a battery to the other end with a wire without anything that has some resistance to it, a decent amount of resistance, the current's going to be huge and you can short circuit the battery. Well, if I had this same battery and the same light bulb, but now I had this wire that was just I just erase that. So I have this exact same battery, exact same. All right, now I'm starting to get annoyed. Exact same battery, same light bulb, but I have a wire which is 20 times longer. Again, if resistance is how hard is it for current to get from one spot to another spot. If I have to go 10 times farther, it's going to be that much harder. So second characteristic is length. The longer the wire, the greater the resistance. And then the very last thing is it depends upon the type of wire. We call this conductivity. Copper has a certain conductivity. Gold has a certain conductivity. Aluminum has a certain conductivity. It's just the number that describes how good of a conductor something is. So for example, in general, copper has less resistance than steel. So if I had two wires that were exactly identical, same length, same thickness, but one was made of copper, the other one was made of steel, the copper wire would have less resistance. Okay, and the very last one overall, it also depends upon heat, meaning resistance depends upon heat. Now, I used to have this really great animation I could show you, but it's not working anymore. But if I heat something up, the atoms and molecules start moving faster and faster and faster. Same is true inside a wire, right? What's happening when you're boiling water? You're adding heat. The heat causes the kinetic energy of the atoms and molecules to increase, and they start moving faster and faster and faster. Same thing is true in a wire. If I have a wire that starts getting hot and heats up, what's going to happen is the atoms and molecules inside the wire are going to start bouncing around and moving faster. It's going to be harder for an electron to walk through. Think about this, again, if I'm trying to walk in a hallway, if everybody's just kind of staying where they are, it's going to be easy to walk through the hallway. But now I put on some kind of heavy metal or whatever you want to do, and people are now bouncing around and moving and doing their little bam, 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 bam. Now, if I'm trying to walk through the hallway, it's going to be a lot more challenging. I'm going to keep getting knocked into. This is what's happening in a wire as a wire heats up. It's going to be harder for electrons to flow from one end to the other. So in a wire, current depends upon the resistance. Resistance depends upon certain properties of the wire. Those properties that matter are, 1, how thick the wire is, 2, how long the wire is, 3, what the wire is made of, but it also depends upon temperature. As things heat up, then the resistance goes up. Okay, so let me pause this for a second. Actually, I want to just pause here. I want to give you a clicker question to think about. But before I do, I want to open it up to questions for a minute or two. Let me stop this for 1 second. Anyone have a question I can answer? Going once, going twice. Okay, let's move on and think about a clicker question. Oh, that's my phone. Oh, group chat. Okay, here is a, let me make this bigger. Okay. So clicker question is this first one. Question. Draw on this. Draw. Question 1. Question is this. Will the current in an ordinary light bulb be greater immediately after it is turned on or a few minutes later? So ordinary light bulb, ordinary incandescent light bulb, you flip the switch and turn it on. The question is, will the current be greater immediately after it's turned on, a few minutes later, or will it be the same in either case?
Where do we vote?
We don't. Actually, I was just gonna say something. You guys have, let me get out of this for 1 second because I need to be able to see. I'll bring this back up. Makes sense. Speaker view, no. Gallery view. Participants. Expand. You guys have a button where you can see, like I just did yes, no, and then go faster. Can you guys see that? Oops. So do people see up near participants? Yeah, people at this, Alice and Alyssa just did it. You can click either yes, no, go slower, go faster, thumbs up, thumbs down, and so on. Let's try this just as a clicker question. Let's just do these in order. Can try to see how this works. Let the yes button be A, the no button be B, the go slower button be C, and the go faster button be D, if we have that many. So then just as a clicker question, try this first one again. Let me share it again. Share screen.
I don't see that option on mine.
Let me stop this for again. So do you have down at the bottom, you may not have a participants window open?
Let's see. Oh, okay, got it.
Does everybody see that there's a participants window, and then down at the bottom, there's little buttons you can press.
Okay, I see it now, thanks.
Okay, so let's go back to this, and I don't know that I'll be able to see it, what people are voting when I'm sharing this screen, and I don't even know how this will work, but let's just try it out. Okay, so the clicker question is, will the current in an ordinary light bulb be greater immediately after it is turned on or a few minutes later? So A, or yes, is immediately after it is turned on. B, or no, is a few minutes later. And then C, I forget whatever one was next to C. Go slower, I think. That would be the current will be the same. Let's take about 15 seconds, think about that. When you have an answer, if you want to share it, then just type in either, or punch in yes for A, no for B, go slower for C. All right, I'm going to stop this share just for a second so I can see what people are voting. We got some B's, we got some A's, we got some A's, we've got some B's, we've got some B's. B was, it'll be greater a few minutes later. Will the current be greater immediately after it's turned on? Okay, so let me go back to this. Okay, so keeping in mind 2 things. Let me make sure I can draw on this. It's gonna be much better. So what we know is current is proportional to voltage. That's not changing. And what we've been talking about with resistance is current is proportional to 1 over resistance, which means when the resistance is small, the current is high. When the resistance is high, the current is low. So think about, when is a light bulb the coolest? A light bulb is the coolest right when you turn it on or before you turn it on. As a light bulb is on for a few minutes, it starts to heat up. As it starts to heat up, the resistance goes up. As the resistance goes up, the current goes down. So the answer to 1 is, it is greater immediately after it is turned on. Why? Because what ends up happening is, as it heats up, resistance goes up, which means the current goes down. So as the light bulb is on and getting hotter, the resistance is increasing, which means the current is decreasing. So the current is going to be greater immediately after it is turned on. And this actually has an interesting consequence. When is it that a light bulb burns out? 99 times out of 100, a light bulb burns out right when you turn it on, because that's when it's coolest. So the resistance is the least, so the current is the greatest. It's very rare to see a light bulb that's been on for an hour or 2 to burn out. It's almost always as soon as you flick on the switch, because that's when the current is greatest, because that's when the resistance is smallest, because that's when the temperature is the lowest. All right, let me stop this again and just open it up. This is kind of an important point that comes up. So temperature affects resistance. As things heat up, the atoms and molecules start moving faster. As that happens, it's harder for electrons to travel through a wire, which means the resistance of the wire goes up. In a normal light bulb circuit, as the bulb is on, it heats up. And so the resistance of a normal circuit containing a light bulb is lowest right when you turn it on, because that's when the temperature is the smallest. As it heats up, temperature goes up, resistance goes up, which means the total current's going to drop. All right, any questions on that particular concept? All right, if not, then I've got, what do we say? It was 9:30 to 10:45. Got another few minutes, and then I'm going to sort of pause this, stop it, and then open up office hours. So let me go back and just see last thing I want to cover. Okay, good. We're in good shape. Ohm's Law. All right, go back to this. Okay, so very last couple minutes I want to talk about and just actually formalize Ohm's Law. I've kind of touched on it a couple times, but I want to just officially cover it. And actually, this is not really a recap. Oh, where's my other hat? Ah, okay. So, kind of went through, resistance of a wire depends upon 3 or 4 characteristics of the wire: the thickness of the wire, length of the wire, what the wire's made of, and if the wire's hot, the resistance goes up. Okay, so last part of this, we measure resistance in a unit called ohms. And an ohm is written as a Greek omega. Draw. And somebody named Ohm was really the first person to sort of study the relationship between current, voltage, and resistance. Hence, he got a unit named after him, the ohm, and Ohm's Law is named after him. So as I've written before, Ohm's Law basically says how much current you get flowing equals the voltage you connect the circuit to divided by the resistance of the circuit. In terms of units, how many amps of current you get equals how many volts you connect it to divided by how many ohms of resistance. Greater the voltage, greater the current. Greater the resistance, smaller the current. Whoops. Greater the resistance, smaller the current. And then just as a little preview, so you can get ahead, I'm going to finish chapter 23 on Tuesday, and then we'll start chapter 24. And then I'll upload the homework or the quiz and stuff for chapter 23 this weekend if I can. Again, just a little reminder, after you do the homework, Mastering Physics is going to say that your score is a 0 because I have to individually check off every single answer. I may not do that through Mastering Physics. I may just download all the homework and just quickly glance at everybody, just put something for each answer. Okay, let me stop this share. What questions can I answer? Any questions on anything related to Physics 10? Going once, going twice. Brian.
You pushed everything just a day later, right?
Say that again?
Like for like the assignments that we had, like whatever was due today is due tomorrow, and then whatever was due tomorrow is due Saturday.
Yeah, I pushed everything back by a day. So yeah, I think the homework's due by Friday, quiz by Saturday.
Okay.
But again, those dates are the final drop-down dates. Like we've been done chapter 22 for a while.
Right,
so
yeah.
Don't wait until the last minute and then.
No, I already did. I was just asking.
No, I'm not saying you are. I'm just saying this.
Because there was in the introduction to master physics stuff, like that one's also set for tomorrow, right?
Correct.
Okay.
All right. Any other questions? Omar,
Yeah, I was gonna ask. I'm having a hard time logging on to the course, like McCullen.
Hey, so Omar, check in with me. I have office hours in a little bit, but this is for Physics 10.
Oh, my bad.
Oh, yeah. No worries. I'll see you later. And one, just so you know, I'll send this out as an email. This link is the personal Zoom meeting spot for me. So I use it for all of my classes, meetings, things like that. So if you're ever just clicking on it, it might take you to a meeting I have for a different class or something like that.
Okay, yeah.
Okay, other questions, Physics 10? If not, what I'm gonna do is stop this Zoom and then restart it in about 5 minutes, and that's gonna just be office hours, and I'll answer any questions people have. All right, thank you for showing up. I will post this to YouTube hopefully by the end of the day, but sometime soon, and then I'll send out an email to everybody letting you know that the videos are posted. All right, have a wonderful weekend, and let me end this meeting for all.